Welcome. In this video, we're going to take a deeper look at angular motion by taking a look at angular velocity and angular acceleration. So far in this course, we've talked about planar motion, and that's how all of our kinematics are going to be. They're going to be movement in a plane. And up to now, we've talked about linear motion on the plane, so straight line motion that's confined to the plane. And in this video and in this section, we're going to talk about rotation in planar motion. So even though the plane has an x and a y coordinate, the axis that you have any rotation in planar motion comes around an axis that is perpendicular to the plane. So in this case, it would be looking like it was coming out of the screen at you. That would be the rotation axis. So an object would rotate around that axis. And in planar motion, that's the only axis anything can rotate around. So it makes it a little bit simpler, but we still need to define for rotation, we need to define what a positive and a negative rotation are, because we can rotate one way or the other. And typically in planar motion, when you have an xy coordinate system like we've got there, we define a positive rotation as in the counterclockwise direction. So you can see on that arrow, we have a circular arrow with a plus sign in the middle that tells us that rotation in that direction is positive. And like I said, typically it's counterclockwise. It can be whatever you want it to be, as the coordinate systems are arbitrary, but you do have to define it. You have to show it on your coordinate system. So in this case, a positive rotation would look like this, and a negative rotation would look like this. So first up, we want to take a look at angular velocity. And angular velocity is simply the rate of change of angular displacement with respect to time. Now that should look familiar, because that is exactly the same kind of definition that we used for linear velocity. But in this case, we're just looking at the rate of change of angular displacement instead of looking at the rate of change of linear displacement. It's exactly analogous to linear velocity. And so we've got the formula down there where the average angular velocity is the change in displacement. That's the final angular displacement minus the initial angular displacement over the time. And in this course, we're going to use, obviously, we're going to use theta for angular displacement, but we're going to use omega, the Greek letter omega, which looks like that squirrely W. That's omega, and we're going to use that for angular velocity. Typically, the units for angular velocity could be radians per second and degrees per second. Those are the two most common. And sometimes we use revolutions per second as well. And we'll use an example of that a little bit later on. So to show a simple example of average angular velocity, let's take a look at this baseball bat. And let's say we've swung it through an arc that starts at 40 degrees of angular displacement and ends at 160 degrees of angular displacement. And we swing that baseball bat over a span of half a second. So it takes a half a second to go from the 40 degree mark to the 160 degree mark. So we want to know what is the average angular velocity. In other words, how fast is that bat rotating? What's the average angular velocity across that half second? And so our formula is the change in displacement over the change in time. And so in this case, the change in displacement would be the final would be 160 degrees, and the initial is 40 degrees. So it's 160 minus 40 divided by the time, which is a half a second. And so that becomes 120 degrees over a half a second. And so our average angular velocity of the baseball bat across that half second was 240 degrees per second. Next up, let's take a look at angular acceleration. And again, angular acceleration is exactly analogous to linear acceleration. So angular acceleration is simply the rate of change of angular velocity with respect to time. So in other words, how the angular velocity is changing. We're going to use, in this course, we're going to use the Greek letter alpha. It looks like that squiggly looking A. Alpha is going to be used for angular acceleration. And so the formula for angular acceleration, exactly the same kind of thing that we had for linear acceleration. It's the change in angular velocity over the change in time. And again, typically the units are either radians per second squared or degrees per second squared, and occasionally revolutions per second squared, but usually it's just either radians or degrees per second squared. So as you can see, the relationships between displacement, velocity, and acceleration for angular motion is exactly the same as the relationships that we had for linear motion. And so the angular velocity is simply the rate of change of angular displacement, and the angular acceleration is simply the rate of change of angular velocity. So those relationships are exactly the same. So if you have an angular displacement graph and you want to find angular velocity, you're looking for the slope of that graph. Same thing if you have an angular velocity graph and you're looking for angular acceleration, you're looking for the slope of that graph. And exactly the same thing if you're going the other way. If you have angular acceleration data and you're looking for velocity, or if you have velocity data and you're looking for displacement, you're taking the integral. So again, those relationships do not change. We're still talking about displacement, velocity, and acceleration. The only thing that's changing is we're talking about things that are rotating instead of things that are going in a straight line, but those relationships between those quantities don't change. So if those relationships don't change, then we can take those constant acceleration formulas that we had for our linear kinematics and we can use them in our angular kinematics, because those formulas are simply based on those relationships between displacement, velocity, and acceleration. And if those relationships don't change, then these formulas don't change. So the only thing that's really changed in these formulas is the symbols. So we've taken all the d's for displacements and replaced them for thetas for angular displacement, and the v for linear velocity and replaced it with omega for angular velocity, and the a for linear acceleration and replaced it with the alpha for angular acceleration. But otherwise the formulas are exactly the same. Again, because those relationships between displacement, velocity, and acceleration don't change simply because it's rotating. So an example using those constant acceleration formulas would be something like this. So we've got a figure skater, and she's spinning right now at 1.5 revolutions per second. And then at some point she starts to increase her rate of rotation up to 2.5 revolutions per second. And she does that over a 2-second span. So the question here is asking how many revolutions is she going to do over that 2-second span. So when she increases from 1.5 revolutions per second to 2.5 revolutions per second. So in this question, the initial condition will be the start of that 2-second interval, and the final condition would be the end of that 2-second interval. So the start and the end of that movement that we're looking for. So in terms of initial angular displacement, again, we're looking for displacement over the whole time. So we can set the initial angular displacement to 0 because we're really looking for the change in displacement across from initial to final. And in terms of initial angular velocity, well, if we look at the question, it says she starts at 1.5 revolutions per second. So that would be our initial angular velocity. So the final condition, again, is at the end of that 2-second interval. So when we look at the final angular displacement over that 2 seconds, that's actually what we're looking for. That'll be the answer to the question, is the final angular displacement, or how many revolutions is she going to have over that time. In terms of the final angular velocity, we can take a look at, and it says, the question says that after those 2 seconds she'll be at 2.5 revolutions per second. So that gives us our final angular velocity. And finally, for the kind of the last two pieces of information that we look for in these kind of questions, we're looking for the time, and so we know that this whole question takes place over a 2-second interval, so the time is 2 seconds. And the last thing is the angular acceleration, and we're not actually given angular acceleration, not explicitly. We know angular acceleration had to have taken place because the angular velocity changed. So we went from, or she went from 1.5 revolutions per second to 2.5 revolutions per second. So if the angular velocity changed, then there had to be angular acceleration. But in this case, we don't know it yet. So if we have all those pieces of information, we're really looking for that final angular displacement. And if we look at our four equations that we have available to us, all of them except that last one have angular acceleration explicitly in it, but this last one doesn't. So it looks like we have everything else that we need for that. So we're looking for final displacement. We have initial displacement. We have initial and final angular velocity, and we have time. So we could use that last equation. But we could also, if we wanted to, maybe use the first equation and try to figure out what the angular acceleration was. And then we'd have all the pieces of information other than final displacement, and we could figure it out with another formula. But let's just use this fourth formula here. It's the most straightforward way. And so we have the formula there, so we can plug it in. So the final angular displacement is equal to the initial angular displacement, which is 0 revolutions, plus 1/2 times the sum of the initial and final angular velocity, so 1.5 revolutions per second plus 2.5 revolutions per second, multiplied by the time, which is 2 seconds. So if we crunch that a little bit, we get 1/2 times 4 revolutions per second, that's the 1.5 plus 2.5, times the 2 seconds. And if we run that through, we get a final angular displacement of 4 revolutions. So over that 2 seconds, if she starts at 1.5 revolutions per second and increases her speed, her angular velocity up to 2.5 revolutions per second over a 2-second interval, then over that 2-second interval, she will have performed 4 revolutions. That'll be her final angular displacement.